Show that the relation R on the set of integers, which is defined by the ordered pair x comma y belonging to the relation R if and only if x minus y is divisible by n. This is an equivalence relation on Z. Okay, let us begin. Now, what we have to do here is we have the set of integers Z. If we take the Cartesian product of Z with itself, then we have the relation R being a subset of that Cartesian product. Okay, now what is R here? Now R here is defined as the set of ordered pair x comma y such that x minus y is divisible by n. Fine. And we have x comma y belonging to the set of integers. So this is a relation that has been provided to us. We have to show that this relation R is an equivalence relation on Z, on the set of integers. How do we show that? So that means we have to show that the relation R is reflexive, symmetric as well as transitive on Z. Okay, let's start by checking out if it is actually reflexive or not. Okay, to check for reflexivity, all we have to do is, let's say we consider some element, for any a belonging to the set of integers, we have to consider an integer R. So here we're considering that a minus, so here what is x here? X is something that belongs to the set of integers and y belongs to the set of integers. But instead of considering x and y, we're considering an element a that belongs to the set of integers. So what we do, we replace x with a and this y with a. That gives us a minus a, which is equals to 0. Now the question is 0 divisible by n? Definitely, because we can rewrite 0 as 0 multiplied to n. And since it's a multiple of n, so here we can say clearly that a minus a is divisible by n. This is divisible by n. Now if this is divisible by n, that means our relation is true. In other words, what we can say here, that the ordered pair a comma a definitely is going to belong to the relation R. So this means that our relation R is reflexive on the set of integers Z. So let's write it down. So here relation R, or simply let's write it down, R is a reflexive relation on the set of integers Z. Fine. Okay, so next what we'll do, we'll try to check whether if it is symmetric or not. Now, in order to check whether if it is symmetric, we'll have to take two elements. So let's say we consider two elements, a and b. So let a comma b, these are two integers. Fine. Now if we're considering two integers, so what we'll have to show, that a minus b is divisible by, say, suppose we are supposing that let a minus b is divisible by some integer n. So we're supposing that this is a true statement. Now if a minus b is divisible by n, so can we not say that a minus b is simply a multiple of n? So here we can represent a minus b as lambda times n, where we are considering lambda to be some integer. We don't have to worry about this value, it's some integer. So a minus b equals to lambda and simply tells us that a minus b is divisible by n. Now let's do one thing. So let's take negative as the common factor, or we can say let's multiply both sides with -1. So that's going to give us b minus a equals to negative lambda times n. Okay, so we can rewrite it as b minus a equals to beta times n, where we are considering negative lambda to be equals to beta, which is also some integer. We don't have to worry about the values of lambda and beta. All we have done is replace negative lambda with beta. And what does it tell us? This simply tells us that b minus a is divisible by, this is divisible by n. So here, when we say that a minus b is divisible by n, if we try to write this in terms of an ordered pair, the relation in terms of an ordered pair, all we have is chosen A and B. The ordered pair A and B is chosen in such a way such that A minus B, the relation between A and B is that A minus B is divisible by N. And what did we get here? Here we were able to get another ordered pair which also belongs to the same relation R, that is B comma A. So here we were able to show that B comma A is also a member of this set. Right? So this is only for understanding. This is not how we write. This is only for understanding. So this actually B minus A is divisible by N simply means that B comma A, this ordered pair, also belongs to the relation R. So we started out by considering A minus B is divisible by N, meaning we say that A comma B belongs to the relation R, and we are able to show that B comma A also belongs to the relation R. So this simply means that R is symmetric. R is symmetric on the set of integers. Okay, now let's go to the final one where we will try to show that R, the relation R is transitive. The relation R is transitive. Okay, so for this, what we'll do, we're going to consider three numbers. So let's say A, B, and C belongs to the set of integers. Here we are considering A comma B belonging to the relation R and B comma C belonging to the relation R as well. What does that mean? A comma B belonging to the relation R simply means that we have A minus B divisible by, this is divisible by N, and B comma C belonging to R simply means that B minus C is divisible by, B minus C is divisible by N as well. So A minus B is divisible by N and B minus C is also divisible by N. A minus B is divisible by N simply means that A minus B must be equals to lambda times N, where we are saying that A minus B is simply a multiple of N, and B minus C being divisible by N simply means B minus C equals to beta times N. Okay. So let's specify what lambda and beta are, where lambda comma beta are some integers. We don't have to worry what they are, but they're just simply integers. Okay, so we have A minus B equals to lambda n and B minus C equals to beta n. So let's do one thing. So from here, let's isolate B. B is going to be equals to A minus lambda n. Fine. And we're going to use this value of B and substitute into this equation such that we get A minus lambda n minus C equals to beta times n. So that gives us A minus C equals to, so we transpose negative lambda n to the right hand side to get lambda n plus beta n. That's now giving us A minus C equals to lambda plus beta multiplied to n. Or we can say A minus C equals to gamma times n, where lambda plus beta, since lambda is an integer, beta is also an integer, there must be some integer which we are representing with gamma. So here we have gamma which belongs to the set of integers. So we were able to show that A minus C is also a multiple of n, or in other words we can say A minus C is divisible, this is divisible by n, or we can say A comma C belongs to the relation R. So what we have done, so we have shown here that if A comma B belongs to the relation R and B comma C belongs to the relation R, then we were able to show that A comma C also belongs to the relation R. And what does it tell us? This simply tells us that R, the relation R, is transitive. R is a transitive relation on the set of integers Z. So this shows that, hence we can finally say, that R, since it is reflexive, symmetric and transitive, so R is an equivalence relation. So it's going to be an equivalence relation on the set of integers Z.